Okay, well, the plan for today, if everyone can hear me, is I'll give everyone a few more minutes to join us, as we don't have a full complement of students. This morning, I'm going to discuss consolidation, and that will take us about an hour and 15 minutes to an hour and a half. After that, I'll talk about consolidation testing, data analysis. That will take us about an hour. If people want, I can go over external loads after that. I did put some video solutions on Learn for you guys to review. If people had questions on the video solutions, I can answer those questions. And then finally, at the end of class, you guys will be able to review your test number 1. So I did give a brief summary of common mistakes that I observed on test number 1. So please take a look at those and see if those apply to you. You won't be tested on any of this material again. So none of my tests are cumulative. So once you're tested on material, you don't have to remember that material moving forward. That being said, stress profiles and total effective stress, pore water pressure, that's a concept that we build on moving forward. So if you're a little unsure of that concept, please don't hesitate to contact me, and I'm more than happy to work with you on that concept. Okay, we're getting a few more people. I'll give everyone 2 more minutes, and I'll start at 9:05. Wonder if it's because they're going to my cell phone. This will work. Okay. Okay. Yeah, I don't know. This WebEx is a funny system. Some mornings it works seamlessly, and other mornings it does not. I know this morning I froze for probably 3 or 4 minutes. I tried to log in early to avoid, like, logging in at the same time as everyone else in the neighborhood. And then just before 9 o'clock, when everyone else would have been logging in for their work or school or whatever, my computer froze. So, okay, I'm going to record the lecture. Okay. So if you can't send messages to the group, can you guys send messages to me? Because some of you are able to obviously text me privately. Yeah. So if you have any questions, just send it directly to me, because it doesn't go through to the group, and I'll try my best to answer the questions. If there's something you would like to talk or discuss with me privately, we can discuss that after class. So I'm going to begin recording now. So today, as I mentioned, we're going to talk about consolidation and the theory behind consolidation. Then we'll talk about consolidation testing. I'll answer any external load questions, and then we'll have an opportunity to review our tests at the end of class. So consolidation. So why is consolidation important? Well, consolidation is important because it helps us estimate the magnitude or the amount of settlement that will occur and the rate at which the settlement will occur. So especially in the Red River Valley and in southern Manitoba, this is a very important concept. I've worked on a couple of projects where we've had to modify the design because of consolidation or settlement that may occur. I worked on the St. Adolphe Ring Dike expansion project in St. Adolphe. We constructed a 4-kilometer extension to the ring dike there. The ring dike was over 3 meters in height, and we had to determine how much settlement was going to occur. And based on that settlement, we had to overbuild the dike slightly to ensure that the dike had sufficient freeboard in case of a flood event. So I believe the estimation of settlement was in the 6 to 8 inch range. Settlement in the Red River Valley, because we have a lot of clay material and it's quite thick, it was going to take 260 years for us to achieve 90% consolidation. That's a long period of time, but consolidation doesn't happen instantaneously, and it takes a long time. So 260 years, I won't be around in that time period. Another example, if from those of you who are from the Brandon area, if you think of the 18th Street Bridge, the approach embankment for the 18th Street Bridge was constructed. It was quite a high embankment, but can anyone estimate or guesstimate how much settlement was calculated to occur for that approach embankment? What do you guys think? It's really soft alluvial clay in the Brandon area. It's about 18 meters thick. Anyone want to hazard a guess? No? Okay, 1.1 meters of settlement. So 4 feet of settlement was expected to occur for that approach embankment. So imagine 4 feet of settlement that would occur over a relatively short period of time. So they had to design that approach embankment, taking into account there would be 4 feet of settlement. So in that situation, they had to design so that they would expedite the settlement, because imagine constructing a bridge on an approach embankment that still was going to settle 4 feet. So that's what transpired in Brandon. So this is why consolidation testing is very important, because it helps us determine both the magnitude and the rate of which settlement will occur. Oh, does someone have a question?
Yeah, was that due to the heat washing out all the time and the whole mall area getting flooded?
Yeah, so exactly, Kelly. So the alluvial material in the Brandon area is it's on a floodplain. So from the Assiniboine River there. So what it means is that material hasn't been consolidated by a glacier. So it's material that's been deposited by a river system, and it hasn't been overridden by something that's heavier. So that's why that material isn't as stiff, say, as the material that you would see in the Red River Valley. Exactly. Okay, same with if you look at the floodplain material up by Lake Manitoba. The alluvial material up by Lake Manitoba, it has a large amount of settlement that you would expect as well, because it's a normally consolidated material, which means it hasn't been overridden by something that's heavier. So there hasn't been a glacier that's overridden it. So it's typically very soft material that when you apply a load to it, it settles quite a bit. Okay, I'm going to do a bit of a demo this morning. Usually when we're in class, the demo is a little bit more exciting because you each get a bag of chips. But because we're not in class, you can pretend like I gave you a bag of chips. But, you know, it's 9 a.m. So I'm going to use this bag of chips as my analogy for settlement. So if you take a look at this bag of chips here, just imagine the air that's in this bag of chips is actually not air, but it's water. So we have this bag of chips. There's some chips in the bag which represent soil particles, and the void spaces are filled with water and not air, as shown by this bag. Okay, so what happens when I apply a load to this potato chip bag? What happens? I apply a load and I release the load. What happens to this potato chip bag? Anyone? I apply the load and I release my hand. What happens?
Either the bag pops or it just goes back to where it was.
Right, it bounces back. So I didn't apply enough load for the bag to pop, but I did apply enough load for the bag to rebound or bounce back. So this is immediate or elastic settlement. So this is exactly, Fabian, this is elastic settlement. So it's this settlement that happens right away, but with this settlement, you don't have any drainage of the water that's in your pore or void space. So this settlement's due to the compression of the water and the soil grains, But what elastic means is if I remove the load that I'm applying to it, then the compression is fully recoverable. So this is what elastic settlement is. So I'm going to have to pop a hole in my bag of chips. No worries, my husband and kids can eat this. So now I've applied a couple, use my compass. So now I'm going to apply a load to my bag of chips. Can you guys see what's happening to my bag of chips? As I'm applying this load, what's happening to my bag of chips? Maybe I didn't pop enough holes in them. Okay, right, my bag of chips is deflating. So my bag of chips is deflating because imagine instead of air in my bag of chips, I have water. So this water is being expulsed from the void spaces within this bag of chips. So this is what consolidation, or sometimes you might hear it referred to as primary consolidation, is. It's consolidation that occurs after the elastic settlement, but you're having excess water expulsed from the voids of your soil, and you're having some compression of your soil grains. So as the water is being expulsed from that void space, your void spaces are decreasing in size. So this is what consolidation is. It's sort of the transfer of the excess pressure. So initially when I apply the load, all of the excess pressure associated with that load is associated with the pore water or the water that's in the bag. But as I keep applying the load, that excess pressure associated with the load is being transferred from the water to the soil particles as the water is being expulsed from this bag. Imagine if the air is the water. So I'm having that transfer of that extra stress from the water to the soil. And I'm having some collapse. I wouldn't say it's collapse, but I'm having a reduction in my void ratio as I'm expulsing water from that void ratio. So that just means as I am doing that, my void ratio is decreasing. So what happens when I apply my load for a sufficient amount of time that I've expulsed all of my water from this bag of potato chips? So that means that your consolidation or your primary consolidation has ended. So 100% of the excess pressure that was generated by this load that I'm applying has been dissipated. And you've had a transfer of all of that stress from the pore water to the soil grain. But my load's still there. So as I keep, I'll just answer that in a second, Fabian. So I'm going to keep applying pressure. So can you guys hear this as I keep applying the pressure? What do you guys hear? Hopefully. Yeah, snack, crackle, pop, right. So this is the continued settlement that's occurring. So this is the settlement. It's called secondary compression or creep. So this is the settlement that occurs over time. Even though all my excess pore water pressure has dissipated, I'm still having some continued settlement. And that's caused by the soil grains sliding over one another as I'm still applying that load. So that's why you can hear sort of still the snack, crackle, and pop. So that is what secondary compression or creep is called. So when we do our consolidation calculations, we're just calculating what our immediate or elastic settlement is and our consolidation settlement is. We're not actually calculating what our creep or secondary compression is. There's a way to do that. We're not going to focus on that in this course. But when designers are designing for consolidation, they design to either 90% consolidation or maybe 100% consolidation, but there will still be some creep or secondary compression that does occur over time. But it's generally much smaller in magnitude than what your immediate settlement would be in combination with your primary consolidation. So the majority of your settlement occurs through immediate or elastic settlement and your primary consolidation. Okay, the water. So is there any questions regarding this this demo? Unfortunately, you don't have your own bag of chips to eat after we did this demo, but hopefully it was able to convey a concept using just something you would have around your house.
Volcano is better.
Oh, you liked my volcano from last year better? Do you guys remember me from last year where I had the Diet Coke and the Mentos? I'm the same person. Okay, so Fabian's question. The water close to the surface, yes, it can go to the surface, but does the water pressure just slowly release into other void particles at greater depths? So what the water pressure does, Fabian, is it transfers from the water into the soil particles. So it's a transfer of stress at the greater depths. It does take, depending on what the thickness of your clay material is, sometimes it takes a really long time for that transfer of stress to occur. So the thicker the clay material you have, the longer the amount of time that it takes for that pore water pressure to dissipate and that transfer of stress to occur. Inherently within lacustrine material or alluvial material, you may have thin seams of sand or silt within that material. And if you do, those are great pathways for your excess pore water pressure to be dissipated. And that may help expedite the consolidation process. Okay, I'm now going to share my screen. Yeah, Ken's retiring. They are looking for someone to teach terrain analysis. They wanted to know if I wanted to teach that. So I made a condensed slideshow and I can upload it onto Learn for you guys if you like. So you should be able to see the slideshow. Let me know if you can't. Can you guys see the PowerPoint?
Is Ken retiring from his job at Trek too?
I don't think so. I think that one's probably harder for him to give up. He's also the editor of the Canadian Foundation Engineering Manual, so that takes up a lot of his time. But he's a big diver. He got into diving quite a bit, so I know he wants to spend a lot more time doing that, especially in the winter, and I don't blame him.
I mean, he probably doesn't need to earn. He probably doesn't really want to earn that much more at this point. Probably just wants to relax and enjoy his life.
Yeah, and I don't blame him. Yeah, he probably is presenting at Niagara Falls, Pavel, because he writes or co-authors quite a few papers, and then he also would be presenting on the Foundation Engineering Manual as well. He's a super nice guy. I really like him. So I don't know who's going to be teaching terrain analysis. Okay, so now we're going to talk about consolidation testing. So the first 6 slides are basically words describing what I visually showed you. So you guys can take a look through those slides on your own. And then if you have any questions, don't hesitate to approach me. So now we're going to talk about consolidation testing. Obviously, we can't determine the magnitude or rate at which consolidation would occur without conducting a consolidation test. So this schematic here just shows you the apparatus that we use to conduct the consolidation test. So you put an undisturbed or a relatively undisturbed sample from a Shelby tube into a piece of or an apparatus called an odometer. Some people call it a consolidometer. I refer to it as an odometer. Your soil specimen in that odometer has a porous stone above and below it, so water can drain both upwards and downwards. So when your specimen's in the consolidometer, it's restrained laterally and it's loaded on the top vertically in different stress increments. So you apply a 1 kg load, the next day you would apply 2 kg, so it's just cumulative. So 1 kg, 2 kg, 4 kgs would be your total loads applied. And you would do this until you go up to about 32 kg, and then you would start to unload at that time period. You have to maintain each of those loading increments until all of the excess pore water pressure has dissipated. So we assume with our apparatus that it takes approximately 1 day. So on day 1, you would load with a 1 kilogram total vertical load. The next day, 24 hours later, you would come in and you would add another 1 kilogram to have a total of 2 kilograms of vertical load. The next day, you would come in and add another 2 kilograms to go up to 4 kilograms. So that's sort of how consolidation testing occurs. As I mentioned, you can have drainage of water in both the upwards and downwards direction. And you record your change in the height of your specimen in the odometer about every 5 minutes or so that you'll record that. You record data more frequently when you initially apply the load. So when you go in and initially apply the load, I believe you record at 15 seconds, 30 seconds, 1 minute, 2 minutes, 4 minutes. And then after that, a reading is taken automatically at every 5 minutes. So as I mentioned, what you're measuring with a consolidation test is the change in the height of the specimen. So by knowing that change in the height of the specimen, you can determine your change in void ratio associated with each of those vertical loads that you're applying. And then you would prepare a plot of your change in void ratio versus your log vertical stress. You can also use this data to calculate both the magnitude and rate, and we've talked about that. And we also talked about you have to have a relatively undisturbed sample. So you would either take a sample from a Shelby tube, or you can prepare a remolded specimen and put it in a piece of equipment similar to in shape to a Shelby tube, and then extract that and do consolidation testing on that. A consolidation test is slightly different than both your direct shear and your unconfined compressive strength tests. That's because the consolidation test isn't a strain control test. We're not using the load frame, and we're not applying a load at, say, 1% of your specimen length or 1 millimeter a minute. So a consolidation test is we're applying a load using the hanging masses, and we're measuring the compression. So that's why a consolidation test is referred to as a stress control test, because we're applying a vertical load, and we're applying a different vertical load every day. This is just if you were to plot your consolidation data at the end of a test, this would just show you, you would use your LDS to measure the change in specimen height. So that would measure your compression, and then time is just time measured from the start of the test. And this plot here just shows you that your vertical stress changes on a daily basis because you're increasing the applied vertical load. At the 280 kPa mark, obviously it's longer than a 1 day time period because each of your major grid lines represents 1 day. And likely that was data that was collected over a weekend. So we never expected the students to come over a weekend and collect the data. So that's why the 280 kPa has a much longer time period than the other vertical loads that were applied. And this here is just an example of a plot of change in height versus your log vertical stress. So I'm going to pause there and give you guys an opportunity to ask any questions.
Answer questions. Is this like a test?
No, sorry, I meant ask questions. There's no test. Well, you do have a test on or quiz on consolidation testing, but you won't do it until after the lecture today. So.
It's today.
No, it's not due today. It's not due for another 6 days, but I assume no one would be doing it until after today. Okay, when the data is plotted, I believe it goes to 0 at the beginning. Do you mean your compression, Fabian? Yes. So you'll see your compression should always be 0. So if you see on this plot here, the compression was initially 0. Then initially you had a little bit of compression that occurred. And then what ended up happening was you had some swelling. And the reason why you had some swelling was because when you're conducting the consolidation test, you saturate your specimen, but your specimen that you're putting in that odometer or the consolidometer, it may not be 100% saturated. So as the water is applied to the specimen in the consolidometer or the odometer, you may have some expansion or swelling of that specimen. So you may actually be getting an increase in your void ratio and a decrease in density as you have some swelling. So your compression may initially actually go below zero in some instances because you're actually having some swelling of the specimen. The reason why that happens, or you might see a negative number, is because we zero the LDS to the very first reading. So whatever your specimen was when we started the test, then that's why it occurs. That would be zero. So if you have some swelling, your compression may show a negative number initially, and then it would go back positive. Anyone else have any questions about consolidation testing or the general theory behind it, process? No, okay. So now we're going to get into some terminology for consolidation testing. So consolidation tests, obviously we use it to calculate the magnitude and rate of settlement. But we can also determine other parameters that are used in determining the magnitude or rate. So the first one is something called a compression index. So you might see something with a C and then a subscript C, and this is your compression index. So what your compression index is it's used to calculate the amount of soil compression that's going to occur. So that's what your compression index is. Compression index is usually used to calculate the amount of settlement on a normally consolidated soil. And we'll talk about that definition in a few minutes. CR is your recompression index. And like it's CC, it's used to calculate the amount of soil compression. But this is for a soil that's been previously loaded. And I'll have a few schematics that will show you the difference between where you calculate your CC value and where you calculate your CR value. The terminology, and we'll use this quite frequently moving forward. Yes, recompression is that are added after. Yes, so Fabian, recompression is where you load your specimen to 32 kilograms, and then after you've left it at 32 kg for a day, you start taking off your weights. So then you would only have 8 kilograms on your lever arm, and then you would remove more weight so that you would only have 2 kg on your lever arm. Yeah, so it's just the reduction in weight. So sigma prime PC, you'll see this a lot moving forward. And sigma prime PC is referred to as your pre-consolidation stress. So pre-consolidation stress is the largest stress that a soil has ever experienced in the past, or it may be the largest stress that it's experiencing presently is the largest stress it's ever experienced. Don't worry about M subscript V. CV is your coefficient of consolidation, and it's used to calculate the rate at which settlement occurs. And CV, the units for CV are typically millimeters squared per minute. The units for your pre-consolidation stress are kPa because it's a stress, and CC and CR are dimensionless. I'm not going to go through all the assumptions used in consolidation analysis. You guys can read these on your own. I would say the two most important are the soil is always considered to be saturated and that you can have flow in the upwards and the downwards direction. This slide here, what I just want you to sort of grasp from this slide here is that when you're having water that's being expulsed from your soil, as the water's being expulsed, your change in the height of your specimen is increasing. So as you're expulsing water from the void space, you're having some collapse of that void space, or the void space is decreasing. So as that void space is decreasing, you're expelling more water from that void space, and the amount or the change in height that you measure for your specimen is increasing. So you'll notice as you plot your 8 kg, or starting at 1 and working up to 32 kg, the amount of compression at 1 kg is obviously smaller than the amount of compression that you would see at 32 kg. So as you increase your vertical load, you would expect to see a greater change in the height of the specimen. And this also means that more water is being expulsed from the pore space or the void space.
Elena,
Yes.
that stuff we had to do last week after the test, is any of that on the quiz?
On the consolidation quiz?
Yeah.
No.
No?
So that external loads? No.
Okay, so are we being tested on any of that stuff?
You will be on your next test on March 26th.
Okay.
So the quiz that you would have that you don't have to complete until next Thursday is solely related to consolidation testing. So it would only be related to the material that I provided you on Learn with the lab data sheet, making sure you understand how the analysis of the data was done, and the spreadsheet that I provided you as well that shows the plots of change in void ratio versus log vertical stress. That's what I'm quizzing you on, is the actual consolidation test.
Okay.
Yeah, not the material you worked on after the test last week.
Okay, thanks.
Yeah, it's just similar to the other lab quizzes that we've written. I believe it's at a 6. So it's a little bit smaller of a quiz than the other ones.
And for test 2, that was the 26th of March at 9 a.m.
Correct.
Okay,
And it's a much shorter test. It will only be 2 hours in duration. And it will only be on the material from modules 9 through 11. So nothing's cumulative. I'll send an email about that as we get closer to the time. Okay, vertical stress. So the log vertical stress is always an effective stress. So just think of it in the sense that all of your excess pore water pressure has dissipated in the scenario when we're doing the consolidation testing, because we leave the vertical load on for a sufficient time period that this can occur. So just remember that your vertical stress is always an effective stress, because we do consider pore water pressure, but we've just given a sufficient amount of time for that excess pore water pressure to dissipate. Okay, so some important definitions that are critical, or I'll say critical definitions, when we're considering consolidation testing, and also when we're doing our settlement calculations, are listed here. So pre-consolidation pressure, we already went over that, but that's the highest stress that a soil has ever experienced. So if we think about the Red River Valley, the clay material in the Red River Valley is considered over-consolidated. And what I mean by that is that clay material was, in the past, it was exposed to additional weight from a glacier. So that clay material has had a higher load on it in the past than what it does presently. So your pre-consolidation pressure is what was the load that was applied to that clay material in the past. So that's what your pre-consolidation pressure or stress is referring to, is that what was the highest stress value that that soil has ever experienced. And that would be associated with a load or an external load that was applied from either a glacier. It could be because you preloaded a site because you were going to do some construction. It could be because you drove some heavy equipment over that. Say one, how do you find that out? Because you can determine that from your consolidation testing. And I'll show you how you can determine what your pre-consolidation pressure is. It could be from heavy equipment driving over it, or any sorts of other anthropogenic influences, lowering or raising the groundwater table, that sort of thing. A normally consolidated soil is a soil that is currently at its highest pressure that it's ever experienced. So we'll think about that alluvial material in Brandon. So that alluvial material in Brandon, that would be material that's adjacent to the Assiniboine River on the floodplain that goes through Brandon. That material is deposited on an annual basis as the river floods. So that soil there hasn't been experienced or hasn't been subjected to a higher pressure or a higher load from a glacier or any other influences. So that material would be considered normally consolidated, because the current state that it's in is the highest pressure that it's ever experienced. If we think about an over-consolidated soil, what an over-consolidated soil is a soil where its current stress level is less than the pre-consolidation pressure. So what that means is the soil has previously experienced a higher pressure or stress. So if we think about the Red River Valley clays, we know that those Red River Valley clays were subjected to glacial loads in the past. So we know that those glacial loads were the highest stress that that soil has ever experienced. So that was its pre-consolidation pressure. But we know that those glaciers have melted and retreated, and that external load's no longer being applied to the soil material now. So its current stress state is less than its pre-consolidation pressure, or less than the stress state when the glaciers were applying the load to the soil in the Red River Valley. So we would constitute the Red River Valley clay material as an over-consolidated soil. And then your over-consolidation ratio is the ratio of your pre-consolidation pressure divided by your current stress state. So if I know what my pre-consolidation pressure is, I can divide it by its current stress state, which is typically its overburden pressure, and then I can determine what the OCR ratio is. For a normally consolidated soil, your OCR ratio is always 1 because its pre-consolidation pressure is the same as its current stress state, because that soil hasn't experienced a higher stress level in the past. Where if you had an over-consolidated material, an over-consolidated material, your over-consolidation ratio has to be greater than 1 because that soil has experienced a higher stress state in the past. I have a schematic in the next slide to demonstrate that, but I think I'll pause here and see if anyone has any questions. Okay. Okay, well, I'll move on to your consolidation curves or consolidation curves. So consolidation curves generally have 2 parts. They'll have the initial slope. So your consolidation curve, to determine or to plot your consolidation curve, you plot your void ratio versus your log effective vertical stress. So that's what's shown on the PowerPoint slide here. So there's 2 components to your consolidation curve. So you can see the first component is that line that's identified in blue. And so that is the slope of your log stress versus E is very low. So you'll see that this slope right here, so along this blue line right here, oh, red's not a good choice, but along this blue line right here, your slope is quite small. So that is the initial portion of your consolidation curve. If you look at the next portion of your consolidation curve, it's at a much higher stress. And typically the slope becomes much larger or much greater. And that's this red line right here, which I've highlighted in yellow. So this is the second portion of your consolidation curve. So the initial portion is quite shallow. So it has like a slope like this, whereas the second portion is quite steep and it has a much larger slope. The pressure where these 2 slopes intersect, so where that red line and that yellow line intersect, the pressure where those 2 slopes intersect is called your pre-consolidation stress. So say one was, how do you determine what your pre-consolidation stress is? That's how you determine. You plot the results of a consolidation test, you draw a line along the portion of the upper portion of your consolidation curve and a line along the lower portion of your consolidation curve, and where those 2 lines intersect is your pre-consolidation pressure. You obviously have to draw a vertical line up or down to your effective stress axis, but that's how you determine what your pre-consolidation pressure is. I'm going to pause there to see if anyone has any questions about how you would determine what your pre-consolidation pressure is. Can you guys hear me? Okay, no questions? Okay, So you're probably wondering, well, how do I determine what my compression index is and how do I determine what my recompression index is? So the steep portion or the second portion of your consolidation curve is the data that you use to calculate your compression index. So it's simply just calculating the slope of the steep portion of your consolidation curve is how you determine what your compression index is. And I'm going to use another slide to demonstrate how you would determine what your recompression index is. And we'll go through an example of how you calculate both what your compression index is and what your recompression index is, probably in the second half of the class. This slide, slide 19, I'm not going to spend any time on. It's another way in which you can calculate what your pre-consolidation pressure or stress is. That's the way I was taught when I went to school. It's neither right nor wrong. It's just another way to determine what your pre-consolidation pressure is. I just provided it in case any of you are going on to Lakehead, and that's the methodology they request that you use. So you can use it as a reference, but I don't expect students to calculate their pre-consolidation pressure that way. I just recommend you calculate it according to the example that I provided. Okay, so you're probably wondering, how do I convert my applied vertical stress and my compression into something that's useful? Well, obviously you get compression or compression measurements from your LDS when you're conducting your consolidation test. But obviously your compression, it doesn't represent a change or doesn't represent what your void ratio would be at each of the different loading increments. So there is a formula shown here that we can use to calculate what our void ratio would be. So this formula here, I've outlined in yellow, shows us how you can calculate what your change in void ratio is at each of the different applied vertical stresses. So obviously we know what H naught is because H naught represents the initial height of our specimen. So we measure the height of our specimen prior to it being put in your odometer. Delta H represents the change in the height of the specimen, and this delta H is measured by your LTS. So you know what delta H is and you know what H naught is. The only parameter in the equation that you don't know is this E naught value. So this E naught value, you actually have to calculate what that E naught value would be. So you're probably wondering, how do I do this calculation? So I'm going to demonstrate that to you guys. It is 9:45. Did you guys want a bit of a break before we go into some calculations? Yeah, okay. Well, let's take a 10-minute break and we'll come back at 9:55 and then we'll do some calculations for half an hour or so, and then we'll move on to some different, some other data analysis as well. So we'll come back at 9:55. Q, you'll find this interesting. So Lakehead and U of M are kind of funny. U of M will give you credit for my course, so you actually don't have to take it. Geotech courses at Lakehead, there'll be your introductory to soil mechanics, which you have to take because Lakehead will not give you credit for any third-year courses. So if you go to Lakehead, you'll be repeating soil mechanics at Lakehead, but from what I understand is it's basically just a repeat of the course that I'm teaching you, so students don't find it overly difficult. The next course would be foundation design. I do a lot more foundation design with the structural engineers, so I have a whole course dedicated to foundation design. I heard no. The issue with U of M is that they don't have a program where you can finish in 2 years. So I've heard unofficially, and don't quote me on this, that U of M actually requires you to take fewer courses, but because they don't have a program dedicated like to college transfer students, it takes you longer to get your degree, but you may only have 3 or 4 classes a term. Whereas at Lakehead, they have a whole program and you go through with other students. Yeah, I don't know how long it is. I know some students last year from structural were going to go to U of M because they had commitments in the Winnipeg area. And I know others went off to Lakehead. Lakehead is done in 2 years plus a bridging program in the summer, whereas U of M might have been 3, maybe it was up to 4, but it was more part-time at U of M than it is at Lakehead. Lakehead foundation design, I teach to the structurals. I don't do as much foundation design with the municipal students, just because I thought there would be other concepts that would interest you guys more. So that concept of foundation design might be a little more. Okay, yeah, Nico was going to U of M, Nico, and there was 2 or 3 other students. I don't have a preference. They're both good institutions. This is what I would say to you guys is, and like, if you want to get your degree, a degree is a degree. It doesn't matter where you get it from. Someone's not going to hire you because you got your degree from a specific institution over another institution. People are just looking that you have your credentials. So I went to a smaller school to get my undergraduate degree, but I took geological engineering, and there was only 4 schools that had it in Canada. Larger institutions, generally, they don't have as much personalized service as the smaller institutions do. But it's just personal preference. I did get my graduate degree at U of M, and I really enjoyed U of M. I haven't been to Lakehead, but all the students I know that have gone to Lakehead have really liked it. So there's no one institution that's better than another institution. There's just different experiences. And it would all depend on the amount of time you want to dedicate. I can't comment on U of M versus Lakehead because I don't know. I did go to a larger institutions, and this is just speaking from my experience. So I went to UBC. So I have a degree in geology and I have a degree in geological engineering. So when I went to UBC, which was a much larger institution, the teaching quality, the instructors or professors were inherently more interested in the research at the larger institutions than they were in teaching. Like teaching was just a byproduct or something they had to do to be able to do their research and be employed at the university. Whereas when I went and got my engineering degree, I went to a much smaller school, and I found the quality of teaching was much better because the professors were more focused on teaching and ensuring students understood the concepts. The class sizes were much smaller. But I don't know the difference between U of M and Lakehead. I can't speak to that. That's just my experiences going to a large institution compared to going to a smaller institution. But as I said, a degree is a degree. Oh, well, that's very sweet. So what I would recommend is you guys talk to students who are going to U of M right now. So if any of you know Nico, I think Nico was going to go to U of M, Paul was going to go to U of M, and maybe Eunice, and from structural, and then Kendra went to Lakehead, Matthew Scott went to Lakehead. I don't know if you guys know them, but they've gone off to Lakehead. So if you do, I would recommend that you reach out to them. How much of a career can you have without a degree? You guys can have a great career with your certificate, or your diploma in engineering. Obviously, you have an advanced diploma in engineering because you've gone through a 3-year program. The differences between your diploma and your degree, you will still advance as a CET. You still have the ability to register with AGM, they're now called, and you would have a limited scope or a limited license to practice. The degree opens up additional doors. You can be more involved in the design process. Sometimes it's easier to climb the ladder of a company if you have a degree, that sort of thing. But you can still, if you have the aptitude, you have the drive, you have the skill, the diploma is not going to hold you back. And it depends if you want to work in consulting or if you want to work in construction. If you want to work in construction, yeah, they're not so concerned with the degree so much. If you want to work in consulting, they'll be more concerned with whether you have the degree or not. They consider the Red River diploma as an advanced diploma because they consider it a 3-year program. So if you look at the courses that you take at Red River, say compared to NATE or SATE or BCIT, you have a much more extensive repertoire of courses than other institutions do. So they can consider it an advanced diploma. And this is what I'd say to you guys. So obviously I didn't go to Red River. I think I've been pretty transparent about that. The thing that I tell my colleagues, which completely like flabbergasts them, is the soil mechanics I teach you guys is the identical soil mechanics that I was taught in university. I've just taken out the derivation of all of the formulas because I never used it in 20 plus years. So if that interests you, I can tell you which direction or which textbook you should read, but I try to more tailor the course to be more of a practical course and not so much on the derivations. Salary range, 50 to 60 range. Is that what most of you are thinking? 50 range? Oh, for engineers are now starting at about 60. When I started out 20 years ago, I was paid $36,000. So salaries have gone up substantially. Not $60 an hour, like $60,000 a year. Engineers don't make $60 an hour, except if you're a senior engineer. So I would say maybe put in 50,000 is maybe what you could say, and then see what they come back as. When you're a senior engineer, you will make $60 an hour. So when you have 20 years of experience, you will make $60 an hour as an engineer. As a technologist, no, you wouldn't make $60 an hour. You would typically probably be more in the $45 to $50 an hour range with 20 years of experience. So there is a difference in compensation. It does take 5 years to get it takes 4 years to get your PEng. PEng, obviously, you're responsible, you sign and seal drawings, and it's in perpetuity. So your estate is also responsible for drawings that you sign and seal. So estates have been sued in the past based on what some people may have considered negligence on someone's behalf. Or incidences that have occurred after someone has passed away. I think there's a statute of limitation about how long you can sue after someone passes away, but so it's 4 years for a PEng. You do get experience, so they will give you up to a year of credit towards your PEng based on your work experience. So you guys would obviously get that year of credit. So you would be down to 3 years to get your PEng once you got your engineering degree. So hopefully that answered some of your questions. Oh, so yeah, Clive, I would be with your 15, yeah. Yeah, but it's still experience, buddy. So I bet down at least 60. No experience is bad experience, in my opinion. It's just different experience, right? So even if it was, surveying experience, it will come in handy. Yeah, I think we digress. So, okay. So this is an example problem 6.4, finding your E0 value or your E0 value. So when I ask you to calculate what your E0 value or your E0 value is, or what your change or what your void ratio would be, this is the process that you would use. The information that I provided on this slide is the exact same information that would be provided to you on a test question. So in this example here, we have a specific gravity of 2.73. So your specific gravity would always be provided. I said the area of the cell is 31.2 centimeters squared. If I didn't give you the area and I just simply gave you the diameter or the radius, you just calculate the area by using the area formula for a circle. The oven dried total mass of the entire specimen is M dry is 85.6. And that value of 85.6 would always be provided to you in the problem as well. And the initial height of the specimen, H0, would also be provided to you in the problem. So in this example problem here, H0 is equal to 18.5 millimeters and M dry is equal to 85.6. And then the formulas that you would need to go through the process and do the calculations are provided on this slide as well. So I'm going to load up my IPvo. So take note of these formulas. These formulas will come in handy when you're doing your calculations. Okay, can you guys see this? Oh, I don't think I've shared my screen. Okay. Are you guys able to see this? Good now. Okay. So this is the same question as the one that I showed you on the PowerPoint slide. The same information is provided. You have your specific gravity, you have the initial height of your specimen, you have the cross-sectional area of your odometer, and you have your oven-dried mass. I've also given you the density of water, and we just assumed it's 1 gram per centimeter cubed. So the very first step in determining your E0 or your initial void ratio value would be to calculate your volume of solids. I'm sure you guys did this. This is something we would see on the lab quiz. No, this is something you would see on your test on the 26th. I will show you, I have another PowerPoint presentation with some calculations that you would see on the lab quiz. What you would be expected to know for the lab quiz would be anything from that lab data sheet that I gave you, and anything from the plotting of the data. So plotting of your void ratio versus log vertical stress. So if I asked you to calculate your CC value, your CR value, what your pre-consolidation pressure is, that's the sort of information that I will ask you on the lab quiz, in addition to other calculations on your lab data sheet. No. So volume of solids is equal to your mass of your dry specimen divided by your specific gravity times the density of water. So I'm just working in grams per centimeter cubed here because I find it easiest to work in that unit. So the mass of your dry specimen is 85.6 grams, and we're dividing that by our specific gravity of 2.73 and the density of water of 1 gram per centimeter cubed. So the volume of my solids is equal to 31.36 centimeters cubed. So that's the first step in my calculation. The next step in my calculation is I need to calculate the height of my solids. So the height of my solids is HS, and that is equal to the volume of my solids divided by the cross-sectional area. So I just calculated the volume of my solids up here, and it's 31.36 centimeters cubed. And I know my cross-sectional area is 31.2 centimeters cubed, and that was given in the problem. So I know that the height of my solids is 1.005 centimeters. So that's the second step. So my final step to calculate the void ratio, I just use this formula right here. So H naught is equal to, or sorry, E naught, or my initial void ratio, is equal to H naught minus HS, which is the height of my solids, divided by HS. So in this problem here, we were given H naught, and H naught is 18.5 millimeters. So the key when you're calculating your void ratio is that you have consistent units. So you can't mix millimeters with centimeters. You either have to have all of your units in millimeters or all of your units in centimeters. I chose to keep my units in centimeters because I've done my calculations for my height of my solids in centimeters. So if my H naught of my specimen is 18.5 millimeters, I'm just going to convert that to centimeters. So it would be 1.85 centimeters. So that's why you see it as centimeters here. The height of my solids is 1.005 centimeters. And then I'm dividing that by my height of solids, which again is 1.005 centimeters. So my initial void ratio, I calculated it to be 0.841. Anyone have any questions how I went through and did those calculations? You would simply just follow step by step, calculating your volume of solids and then your height of your solids, and then you can calculate your initial void ratio. Is the height after? No. So so you mean H naught, Suraj? Oh, HS. So HS would be the height of the solids. No, that's at the start of consolidation for this one, because that's what you're using to calculate E naught with. So that would be your height of your solids at the start of consolidation. Okay, so you can calculate E naught, and then from E naught, once you've calculated E naught, you could determine what your void ratio is at any step of the test. So at any stress level associated with your consolidation test, you could calculate what your void ratio is. So in this example problem here, we're going to calculate what our void ratio is at a stress level of, or at a stress increment of 54 kPa. So this is the formula right here. E is equal to E naught minus delta H over HS. So if I'm looking at it for this stress increment, so E, so this is what I'm trying to calculate, is equal to E naught, and I determined my E naught to be 0.841, and then minus, and then delta H. So these values that are provided are our delta H values. So we have a different delta H value for each of the different stress increments, but you use the delta H value associated with your stress increment. So for this case here of 54 kPa, my delta H value is 0.253. My HS value is 1.005 centimeters, which I calculated up here. And you notice here, your delta H value is in millimeters. So you'll notice in my problem here, I didn't write down 0.253 because that is in millimeters. So I needed to convert from millimeters to centimeters. So the way I convert from millimeters to centimeters is to divide by 10. So it's minus 0.0253 centimeters divided by 1.005 centimeters. So my void ratio at the stress increment of 54 kPa is 0.816. And again, void ratio is dimensionless. So you'll notice with this table here, my initial void ratio is the highest value. And then as you're adding load or adding a stress to the top of the odometer, your void ratio is decreasing as your load that you're applying is increasing. And that's because you're expulsing more water from your void space. So you'll see that your void ratio is decreasing as you're increasing the amount of load that's applied to your specimen. So if you're doing your calculations and you notice that when you do them, that your void ratio isn't decreasing as you're applying additional stress, double check your calculations because something isn't right. Typically with clay as well, most of our consolidation tests are done on clay. Clay, again, would have a void ratio somewhere between 0.8 and I've seen it as high as 1.2. If you're calculating a void ratio in the 0.5 range, likely something's not right. So again, double check your calculations. Don't worry about the CC and the CR for this example problem because I don't want to do it with this one. But is there any questions on how we determined our initial void ratio or how we calculate what our void ratio is at the various stress increments? Okay, I'm going to. Okay. Okay, with this slide right here, what I wanted to show you from this slide is how you calculate your recompression index or your compression index. So you'll see here that this again is a consolidation curve and it's a plot of void ratio versus your log effective vertical stress. So there's two components of your consolidation curve. There's the initial or upper portion of it where you have the slope of the line that's fairly shallow. And then you have your lower portion where your slope of your line is quite steep. So there's two different parameters that you can calculate, your compression index and your recompression index. So your compression index is calculated along the slope of this line here. So if I took this data point here and this data point here, and I calculated the slope of that line using those two data points, that would be a completely acceptable way to calculate my compression index or the slope of the line along the lower portion of the curve. If you wanted to use this data point here and this data point here, again, that's perfectly fine because they're data points that lie along that linear portion of the lower portion of your consolidation curve. So that's how you would calculate what your compression index is, and that's your CC value. So you only calculate your compression index along the lower portion of your consolidation curve or in the normally consolidated range of your consolidation curve. So you know the normally consolidated portion of your curve always lies to the right of your pre-consolidation pressure, right? So this is your pre-consolidation pressure right here, because this is the intersection of those two lines. So your normally consolidated portion always lies to the right of your pre-consolidation pressure, and the over-consolidated portion always lies to the left of your pre-consolidation pressure. So you know that this portion of your consolidation curve represents the over-consolidated portion. So those are two very important points to note. So you use this portion of your consolidation curve to calculate your CC value. And we use generally the unloading portion of our consolidation curve to calculate our recompression index. So generally you'll just have three data points. You'll have a data point here, a data point here, and a data point here. We generally don't do the unloading and then the reloading. We generally just do the unloading. So say you had a data point here and a data point here. The slope of this line is what would be your CR value. In theory, the slope of this line here and the slope of this upper portion of your consolidation curve should be identical. Sometimes they're not. In theory, they should be. But we generally use this portion or the unloading portion of your consolidation curve to calculate your recompression index. And you'll notice that the slope of these lines are much shallower than the slope of this line here for your normally consolidated portion. Any questions? It's a lot, huh?
I guess if our next test is just on 3 modules, you have to make it hard somehow.
The next test isn't hard. Take it from me. Like I told you, the first test was hard, and I don't know if you guys agree or disagree. The next test isn't hard. It's not tricky. It's just doing some calculations.
But do you think we can more work so we can get part marks?
Next test, there is one question where you can submit work for part marks. There's some questions you won't submit work to get part marks. Anything that has a value greater than 2, I accept work for part marks. Anything with a value less 2 or less, generally I don't. The class average for the first one, I think, was around 74, something like that. In that range. Okay, any questions on recompression index or compression index? Okay, let's do an example problem. Example problem 6.5. This is the same example problem that's provided on the PowerPoint slides. This is just sort of worked through. So this is, you have a dry mass of your specimen. This is again representative of a question that I would ask on the test that's being held on the 26th. So this doesn't apply to your quiz that's coming up. So you would have a dry mass of a specimen. It's 106.0 grams. Your specific gravity is 2.74. I've changed the height of your initial specimen to be 22.55 millimeters, and your cell diameter is 63.5. So there's a couple steps to this question. The first step would be you would have to calculate what your initial void ratio is. And once you know your initial void ratio, you could calculate what your void ratio is for each of those different stress increments. That being said, guys, on a test, I'm not going to ask you to calculate your void ratio for all of the different stress increments associated with a consolidation test. I would just give you one line on a test, and I would just say calculate it. I might say calculate your void ratio at the 248 kPa stress increment. So you would only have to calculate your void ratio for this in this column for this stress increment. So you would only have to go through the process and do the calculation once. So one individual might be asked to calculate it at 8 kg or 248 kPa. Another individual might calculate it at 31 kPa, or another one might calculate it at 991. So you only have to do it for one of the stress increments, but you will be told which stress increment you're going to do the calculation for. So similarly to the last problem, you have to go through and calculate your initial void ratio. So you have to start with your volume of solids. So we know our volume of solids is equal to the dry mass of our specimen divided by our specific gravity times the density of water. So we know our dry mass is 106 grams. We know our specific gravity is 2.74. And we know the density of water is 1 gram per centimeter cubed. So I've gone through and I've calculated the volume of my solids to be 38.6861 centimeters cubed. I recommend carrying about 4 sig figs to 5 sig figs when you're going through these calculations. Otherwise, sometimes your E naught value and then your corresponding E values tend to be a little bit off. So carry 4 to 5 sig figs when you're doing the calculations, and then you can do your rounding at the very end. Next step would be to calculate your height of your solids, height of your solids, which is equal to the volume of your solids divided by the area. You know the volume of solids because you calculated it above. The area, I just calculated that by area is equal to pi times 0.063 meters squared divided by 4. Oh, we did it in centimeters. So 6.35 centimeters squared. So if you just go through and do this calculation here, you would get an area of 31.66922 centimeters. So I calculated the height of solids to be about 1.0 221569. I carried a bunch of sig figs with that. So the next step would be to calculate your void ratio. So your void ratio, or your initial void ratio, is equal to the height, your initial specimen height minus your height of solids. So your initial height of your specimen is 22.55 millimeters, and the initial height of, the height of your solids, I converted from centimeters to millimeters. So here I went 12.21569 millimeters. So I just multiplied my centimeter value by 10 to convert to millimeters. So I go through and I do my calculation and I determine my initial void ratio to be 0.84599. So that's my initial void ratio. If I take a look at what would be my void ratio at 1 kilogram mass or at 31 kPa stress increment, I know my initial void ratio is 0.84599 because I calculated it above. I know delta H, so I know my delta H value is 0.099 millimeters. And I also know what the height of my solids are because I calculated my height of solids up here. So my height of solids, I've calculated that value as well. Again, the key is to ensure your units are consistent when you're doing your calculations. You can't mix centimeters and millimeters because your answer is not going to be correct. Here you'll see I've converted everything to millimeters this time instead of centimeters. It doesn't matter which way you prefer to go. Just make sure your units are consistent when you're doing the calculation. So I've gone through and I've calculated my void ratio at the 31 kPa stress increment to be 0.837882. So I would record it as 0.8379. That's how I've recorded it here. So you can go through and you could follow the same process and do the calculations for each of the different stress increments. What I did, guys, was I made a spreadsheet, and from that spreadsheet, that's how I was able to derive the values much quicker. So those of you who are comfortable using Excel, you can use Excel and make a spreadsheet and do the calculations accordingly. It's important that you're able to plot your data to be able to do the analysis. So here I'm going to flip back to this. So I've gone through and I've done all the calculations, and then I plotted the data. So here I plotted the data of void ratio versus my log effective vertical stress. So this is what my consolidation curve looks like after I've plotted the data. So you'll see I have my initial shallow portion of my consolidation curve, or the first portion, and then I have the steeper portion of my consolidation curve. And this is the unloading portion of my consolidation curve. So I just went through in Excel and I made major and minor grid lines so it was easier to derive values. I just changed the scale of my plot somewhat. So from this graph here, I was able to go through and I was able to determine three things. I was able to determine, what do you think the three things are that I was able to determine from this graph? Yeah. So you're able to determine CC, CR, and your pre-consolidation pressure. Yeah, exactly. So to determine your pre-consolidation pressure, you draw a linear line along the lower portion of your consolidation curve. So you'll see here, this line that I've identified in red, this is the lower portion of my consolidation curve. So I drew a linear line along here. And then here is the linear portion of the upper portion of my consolidation curve. So I drew a linear line along here, and I draw over my red line in blue so you can see the difference between the upper and lower portion of the consolidation curve. Where those two lines intersect is what my pre-consolidation value is. So I've drawn a vertical line down in red to show you what my pre-consolidation pressure would be. So this is where, this point right here is where my two lines intersected. I'll draw my line down in yellow, and where this line intersects with my log vertical stress axis, that is how I determine what my pre-consolidation pressure is. So in this instance, it's about 110-ish kPa in that sort of range. Again, I accept a range of values as long as they're reasonable when you're doing the interpretation of the graph. Any questions on how we determine the pre-consolidation pressure? Scroll down. I can't scroll down, Cole. It's not letting me scroll down. Yes, so they are, they're semi-log graphs in the sense that void ratio is not plotted on a log scale, but your effective vertical stress is. So when you go into writing a test, I will provide you graph paper that is a semi-log scale where your x-axis will be a log scale and your y-axis won't. Don't use the ASTM method, just use this method here.
What's the difference between the two?
Really, there's nothing. You might get a slightly different value, plus or minus 5 kPa. I just showed the ASTM method because sometimes that is what they will show you in university. This is what we use in industry, and it's much simpler, but those going to Lakehead, they might show you the ASTM standard method. That's what I learned when I was in university. This one is much easier to do and much faster to do, so I just like this one. You know, plus or minus 5 to 10 kPa isn't really a big deal when you're calculating your pre-consolidation stress. You know, if you're 100 kPa off, yeah, that's a big deal, but plus or minus 5 to 10 kPa isn't a big deal. So I just recommend you use this method because it's much easier. Okay, so the next thing you can calculate is your compression index. So you calculate your compression index by calculating the slope of the lower portion of your consolidation curve. So here I have 3 data points that lie along this linear portion of my consolidation curve. So I can use any of those 3 data points to calculate the slope of that line. So if you want to use this data point here, so this data point, and this data point, that's fine. Or you can use this data point and this data point, that's fine. Or you can use this one and this one, it doesn't matter. Whichever data points you're comfortable using. To calculate your recompression index, you're going to use the data points that lie along this unloading portion of your consolidation curve. I recommend you take this data point here and then this data point here. Because sometimes this middle point is kind of off the linear line. So it's just easier if you take the first data point and the last data point. And that's how you would calculate it. Sorry, Cole, do you have shell? Sorry, Cole, I don't know what you mean by that. Can you unmute yourself and just let me know?
Yeah, I just meant like if you have, you said you put your log calcs into an Excel instead of doing the calculations. Do you have like a shell doc that you have for all of us to use?
No, you can make up your own.
Okay.
But if you want me to check it, I will check it. I'm happy to do that. But if I give you the shell document, what ends up happening is you're just going to input the numbers and then you're not going to understand the process.
That was my plan. That was my plan, but okay, that makes sense.
I know, but I'm happy, Cole, if you make one, I'm happy to double check it for you.
Okay, thank you. You might
Yeah.
have to triple check mine.
But that's okay. I'm okay with that. But I just want you guys to understand the process.
When calculating the slope of a line on a log graph, is that any different than a regular graph?
Yes, and I'm going to show you guys that. Okay, so let's go back. So I don't have my graph on this. I haven't plotted my data points on this graph because I plotted them in Excel and then tried to show them to you guys on the PowerPoint presentation. But when you are calculating your compression index and your recompression index on that semi-log graph, yes, it's a slightly different process. So you'll see here for my compression index calculations, I took the data point at 991 kPa, and then I also took the data point at 248 kPa. So I took this data point here, and I took this data point here to do my calculations. So I need to know what my void ratio is at those two data points and what my stress increment is. So when I'm calculating my compression index, my CC value, it is 0.7304, which is my larger void ratio number. So that would be at the 248 kPa minus 0.58491, which is my void ratio at the higher stress increment at 991 kPa. So that's just the same math that you would normally use when you're calculating the slope of a line. Where it's different is when you go divided by, it's divided by the log of your highest stress increment divided by your lowest stress increment. So I chose two stress increments, 991 kPa and 248 kPa. So it's simply the log of 991 divided by 248. So it's generally like around the log of 4. Here it's 3.995. So it will be just the log of 4. So that's how you calculate the slope of your line using the log scale. So if you go through and do the calculations, the slope of your line here is about 0.243. One thing to note when you're doing your calculations, your CC value should always be larger than your CR value, because your CR value is a fairly shallow slope, whereas your CC, so representing the normally consolidated portion of your curve, is always much steeper. So your CC value should always be larger than your CR value. Yeah, so that's why it's called semi-log, and maybe I phrased that incorrectly. So the E value is like normal, and the vertical stress is on a log scale. But I would give you guys graph paper for a scenario such as that, so you're not expected to go and purchase that type of graph paper. So when you're doing your CR calculation, CC values generally range between about 0.2 and 0.4, especially for clay in the Red River Valley. That's generally the range we see. Your recompression index or your CR value, I use the 991 kPa stress increment and then the 62 kPa stress increment. So I had a void ratio of 0.669001 at 62 kPa, because that's my larger void ratio. And then I had a void ratio of 0.584 at a stress increment of 991. And then again, I just went divided by the log of 991, so my larger stress increment value, divided by my smaller stress increment value, which is 62 kPa. And so my CR value in this situation is about 0.0704. So CR generally ranges, I've seen it range from about 0.03 to just over 0.1. So those are sort of ranges in which you should expect to see your CR value. Okay, any questions? No. Okay. Okay, what would you guys like now? Do you want a bit of a break before I go into consolidation test data analysis? Do you want me to start the theory a bit? What would you guys like? A break. Yep, that's fine. So how long of a break do you guys want? 5 or 10? 10. Okay, well, we can meet back at 10:50. And then we'll start to go through consolidation data analysis. And yeah, and then we'll take it from there. So that should take us about an hour to finish through that section. So enjoy your break, and we'll meet back at 10:50. Okay, is everyone okay if I start? Okay, now it's 10:50. Okay, so now what we are going to do is we're going to discuss how you would calculate what the rate of settlement is. So if we remember, to calculate our rate of settlement, we have to calculate something called our coefficient of consolidation. So I'm going to sort of go through the process of how you would calculate your coefficient of consolidation. So how long does it take for a soil layer to consolidate? So the faster the water can drain away from the soil layer, the faster your consolidation can occur. So higher permeability materials such as sand and silt consolidate at a much, much faster rate than low permeability materials such as clay. We almost assume in a sand material that your dissipation of your pore water pressures is instantaneous. So you would just have immediate or elastic settlement, and you would calculate that for a sand material. And it occurs almost instantaneously. Whereas with a clay material, as I mentioned, it can take hundreds of years for complete consolidation to occur. Your water always needs to drain somewhere. So it either has to drain to the surface or to an adjacent permeable layer. So water always drains faster from the edges of a clay soil than it does from the center of a clay soil. And that's because it has shorter distance to travel for that excess pore water pressure to dissipate at the edge of a clay material than it does in the center of a clay material. So it always takes longer for that consolidation to occur at the center of the clay material. And generally we assume as well that we have a larger magnitude of settlement at the center of a clay layer than we do at the edges as well. So as I mentioned, to calculate the rate at which settlement occurs, we need to calculate something called our coefficient of consolidation, which is our CV value. So each load increment that we have for consolidation test data provides us data at which we can determine the rate of consolidation. So if we had a load increment of 2 kg, 4 kg, 8 kg, my coefficient of consolidation is different for each of those different loading increments. And your CV value isn't constant, or it isn't the same value for a single specimen. So your CV value varies depending on which load increment you're looking at. We generally only calculate our CV values along the normally consolidated portion of our curve. So we generally reserve doing our CV calculations for the 16 and the 32 kg loading increments. So those are generally the two loading increments that we'll calculate our CV value for. There's two different methodologies that you can use to calculate your CV value. One is the log time method and one is the root time method. The methodology and the way you plot the data is a little bit different depending on which methodology you're using. Both methodologies require the thickness or the initial thickness of your specimen. So that's the thickness of your specimen prior to the testing starting, and a t-value. So it could either be your T50 value, so the value or the time that it takes to reach 50% consolidation, or your T90 value, which is the time it takes for your specimen to achieve 90% consolidation. And it just depends on which methodology you're using. I'm not going to spend any time on that one. Okay. The first methodology that you can use, or one of the methodologies that you can use to calculate your CV value. So if you recall, I mentioned earlier that your CV value is in millimeters squared per minute. So this method is called the log time method. And the way you can differentiate between the root time method and the log time method by looking at the plot is your x-axis. So look at this in here, time in minutes, and you'll see a 1, a 10, 100, 1,000, 10,000. So obviously it's the log time method because you're using a log scale. And here, instead of void ratio, you're plotting compression. So your compression is the value that you're plotting. You start at 0, because the very first data point for that stress increment, you would assume that your compression value is 0, and you would compare all subsequent compression values to that very first value that you recorded. So the first one becomes 0, and every subsequent compression value, you take away what your initial compression value. So you're just sort of standardizing it. This is already done for you. So if you were to get a question on a test, I would give you your time increment, and I would give you your compression value. And I would ask you to plot the data, and I would tell you which methodology you would use to plot your data, and then you would determine what your CV value is. So you don't have to go through and do any standardization to get your compression values, and you don't have to determine any time intervals. I would give you all of those, and I would be providing the graph paper. So again, this is the root time method. So with the root time method, you'll see your plot here. It kind of looks like an S. So with your root time method, generally your plot should look like an S. You generally use your root time method for lower permeability material. So such as a clay material, this is the primary method that you would use to calculate your coefficient of consolidation. So to go through and do your calculations, there's a few steps that you need to follow. The first step is, as I mentioned, the shape of your curve kind of looks like an S. So you'll see here, I drew a red line along the middle portion of my S-shaped curve. So that would be the first step that you would do. You would draw a linear line along the middle portion of your S curve. And then you would fit a straight, like a second straight line along the latter portion of your S curve. So the top portion of your S curve where it flattens out. So generally I recommend, say at a time interval greater than 400 minutes is where you would start to draw that second linear line along the upper portion of your S curve. Where those two lines intersect is your T, or is your 100% consolidation. So here, I'm going to change the color. So you'll see here, my red line and my blue line intersect at this point right here. I'm sorry, it's a little bit thick, but you'll see my two lines intersect here. So then I'm going to draw a horizontal line over to my y-axis, and I can see here that my compression at 100% consolidation is 0.78 millimeters. So that's my compression at 100% consolidation. So if I want to know what my compression would be at 50% consolidation, I simply just divide my compression at 100% consolidation by 2. So I would just go 0.78 divided by 2. So therefore, my compression at 50% consolidation is 0.39. So you'll see here, I go down and I would draw a second line. So the second line starts at 0.39 mils, and I would just draw my second line, a horizontal line, until it intersects this consolidation curve, which is S shaped. So you'll see that my H 50% at 0.39 intersects my consolidation curve at this point right here. So then I need to draw sort of a fourth line, and this fourth line is a vertical line down, to my axis, to my log time axis here, and I'm starting this vertical line at the point where my horizontal line intersects the consolidation curve. I'll draw this vertical line down, and I'll see that this vertical line intercepts my time axis at 20 minutes. So this means that the time it takes for my specimen to reach 50% consolidation is 20 minutes. The last line, is it based on the actual reference tree? And I tried my best to have it so that it was straight. So you mean the blue line? Oh, it touches the curve. So it doesn't, you're not drawing it so that it intersects the red line. It's off of the S curve. So your intersection point is off of the S curve. And so, yeah, so your T50 is 20 minutes. So if we went back to this equation right here, so this is the equation that we would use for the log time method. You want to calculate your CV. 0.196 is just a constant. It's always the constant that is used when you're using the log time method. H represents the height of your specimen, so that's given in the problem. And you just calculated what your T50 value was from the graph. So you would just put your T50 value in of 20 minutes. You would know the initial height of your specimen, and you could calculate your CV value. So your height of your specimen, you would have it in millimeters, so your units would be millimeters. So your CV value, you would document in millimeters squared per minute. Your time's always in minutes. We don't convert to seconds, we leave it as minutes. So this is the methodology that we use for the log time method. Any questions on that? So Conrad, the CV value, it doesn't represent how packed the material is. It's trying to calculate how long it would take for your settlement to occur. So how quickly is your settlement occurring? So that's what your CV value is calculating. So again, if I was to give the example of the Red River Valley, it would calculate how quickly does that Red River Valley clay consolidate, maybe compared to that clay material in Brandon. So that's what your CV value is telling you, is how long is it going to take, or how quickly is that clay material consolidating. Does that make sense, Conrad? Okay. If it doesn't, just let me know. I'm willing to re-explain. So again, here's just another example of showing how you would calculate your T50 value. Again, here is a consolidation curve. It's sort of S-curved in shape. The user would go through and draw a linear line along the middle portion of the S-curve. Yes, so it's the intersection of the red and the blue lines for H100. And then a portion along, and then a linear line along the upper portion of the S-shaped curve, and where those two lines intersect is H100. So these two lines intersect here, and then you would draw a vertical line, and sorry, it's me trying to draw a horizontal line over to the vertical axis. So this would represent my H100 value, which is 0.014. So I could go through, I could determine what my H50 value is, and then calculate what my T50 value is. And And from that, you would be able to determine your CV value. So I'm going to pause here before we go into an example as a class. Does anyone have any questions? Oh, okay. I'm just going to do the examples off of the PowerPoint slides because there's a lot of plotting of data. So I just made PowerPoint slides with the example problem. So this is example problem 6.6, and it's asking you to determine the coefficient of consolidation using the log time method. The initial height of the specimen was given, which is 22.5 millimeters. So this is very representative of a problem I would give you on a test. So like a big test, like the one you would have at the end of March, where I would give you the elapsed time, the square root time, and the compression. And then I would tell you to either use the log time or the root time method to determine what your coefficient of consolidation is. It would be up to the student to determine what the appropriate methodology is and go through the appropriate process. So with this example here, you have your elapsed time and you have your compression. So if I'm asking you to do the log time method, obviously you're aware that it would be a plot, a semi-log plot, where time would be on a log scale and your compression would be not on a log scale. So here I plotted the data. So it's a log time, compression versus time. So you'll see here, I plotted the data. So I simply plotted this data here. So I plotted the data that's in this column, and then the data that's in this column here. So the compression is on the y-axis, the time is on the x-axis, but it's on a log plot. So if I go back to here, this is the data as it's plotted, but there's no interpretation or analysis done of the data. It's simply compression versus log time. You'll see I have a log scale, so 1, 10, 100, 1,000, 10,000. Those who prefer to graph in Excel and not use the graph paper that I provide for a test, that's fine as well. It's not a best fit line. What do you mean by that, Huang? Yeah, you just connect the dots. Okay, so here's exactly the same data plotted, but I've gone through and done the analysis portion. So you'll see that with the analysis, I've gone through and I've drawn two linear lines, and they're both represented in red. So I've drawn one linear line, and again, I'm sorry for my unsteady hand, but I have this linear line here that's supposed to represent the linear portion. I don't know, we're just going to delete that. Where's delete on this computer? Okay, well, I'll do my best. This represents the linear portion of the middle portion of the S curve. And this line right here on the top is at a time interval greater than 400. And this red line here that I'm going over in purple represents the linear portion of the upper portion of my S curve at a time interval greater than 400 minutes. So where those two curves, or sorry, where those two lines intersect is your H100 value. So sorry, this shouldn't say T100, it should say H100. So where those two lines intersect, I'm just going to draw a horizontal line over to my y-axis or my compression axis. And my H100 value is equal to 0.67 millimeters. And sorry, this should say H50. So from this H100 value, I can calculate my H50 value by going H100 divided by 2. So if you divide it by 2, your H50 value would be about 0.335 millimeters, or I just wrote 0.34 millimeters. You would follow this purple line, and I draw this purple line over to where it intersects my consolidation curve. And where it intersects the consolidation curve, I drew a green line down, and where this green line intersects my log time axis, that would represent my T50 value. So in this instance here, my T50 value would be 30 minutes. Any questions on how you determine what your T50 value is? And Hong, you could probably, yes, you could probably just use a smooth curve for a line of best fit. But I'm old fashioned, so, but I probably should do that. But. So that's how you calculate your T50 value. I want to pause here, and I want the students to take time to look at the graph to see if they have any questions on the process. Mm-hmm. I'll give you guys 1 more minute to take a look. Anyone have any questions? No.
Sorry, for the CV value, your H, you have 22.5. Where did you get that from again?
That's the height of the specimen. Sorry, Sean.
Oh,
Yeah,
okay.
there's the height of the specimens, 22.5. The 0.196 is just a constant. It's always that value for the log time method. And then the 30 represents your T50 value.
Perfect, thanks.
No problem. Thank you for the question. So I encourage each of you to go through and to work through this problem on your own. This is very representative of what you will see at the end of March. Plot this data, do the analysis for me. You'll have to know how to do both methods. So I do encourage you to go through and have a good understanding of this. Okay, the final method. The final method is the root time method. So this is another method that you can use to calculate your CV value. The calculation is done a little bit differently because you're using your T90 value instead of your T50 value. So the T90 value represents the time it takes to reach 90% consolidation. In an ideal world, it shouldn't matter which methodology you use. Your CV value you calculate using the root time method or the log time method should be the same. In the real world, does this happen? No. The values are usually a little bit different, but it would be up to the lab personnel and the designers to determine which methodology would provide them with the best results. So as I mentioned, generally clay will use the log time method, and with sand and silts with no cohesion, we'll use the log time method. Root time method, you're plotting compression versus the square root of time. So if we go back and say we were to look at the data from this example problem here, the compression data is the same. So you would be plotting this compression data, but you would be plotting your square root of time data instead of your elapsed time. So you'll notice that your square root of time data is simply someone has taken the square root of your elapsed time value. So if I look at, say, I'm going to take a look at a time of 57 minutes. If I am to take the square root of 57, it's 7.55. So this is just simply the square root value of the elapsed time. So that's how they're getting the square root of time on the x-axis. So if I go back to this plot here, square root versus time, it's the square root of your time that you're plotting and not your elapsed time. Compression is the same, so you're plotting your compression data in the same way for both the log time and the root time method. So say, for example, if I had an elapsed time of 57 minutes, I would be plotting it as 7.55. So you'll see that data point data is plotting right about here on my curve compared to plotting my previous graph. It was plotting at 57 minutes. So with your square root of time method, the way you do your analysis is you fit a straight line through your first set of data points, except for your data point at time 0. So don't fit your line of best fit or your line of best fit straight line through your time of 0, but any data point that's larger than 0, fit a straight line of best fit through the first few data points. And you extend that linear line so that it extends higher in elevation than sort of your last few data points. So you'll see here that the test was completed with a compression value of about 0.85. So my plot extends, so it goes up to a compression of 1.0. So I could have ended my plot at 0.9 and that would have been okay as well. But I just draw my linear line of best fit. Here I extended it to a compression value of 1. And I see that it intersects the x-axis, or it intersects this compression value of 1 at a time of 12.2 minutes. So what I'm going to do is multiply that time of 12.2 minutes by 1.15. And it doesn't matter what data you're analyzing, you're always multiplying that value by 1.15. So if I multiply it by 1.15, my new data point over here becomes 14. If I had decided I was only going to draw my line of best fit to this compression value of 0.9, you'll see here that your square root of time value was about 11, and I would have just multiplied that 11 by 1.15, which is 12.65. So you'll see here, I would have just started the second line. No, Fabian, I would always extend, what I would recommend is, you know that your compression value or the last data point you had was a value of 0.85 millimeters. So I would just have it so that it would extend one major grid line above your very last data point. So it won't always be 1 millimeter. It will always, I would just recommend one major grid line above your last data point that you have. So yeah, so if you extended it to 0.9, you could just draw your second data point over here at 12.65, or if you went up to 1, it intersects your 1 millimeter compression line at 12.2 minutes, and if you multiply that by 1.15, you would get a value of 14 minutes. So what you do when you have this value of 14 minutes, you draw another linear line back to that very first data point where you started to draw your initial linear line from. So in this example here, the initial line was in red, and this was the linear line that we're using. So we draw this dashed purple line back to the very first data point on our line, which is here. Sorry for the large font. So that's where you know where to extend this second line back to. Where the second line intersects your consolidation curve, you would draw a vertical line down to your square root of time axis, and that would represent your T90 value. So your T90 value in this case would be 8.3 minutes. But remember, this is the square root of time. Correct. You don't use log graph paper for the root time method. So remember that this data is the square root of time. So if my T90 value from this graph, I think it's 8.3 minutes, it actually represents the square root of T90. So I have to square that value that I've determined. So if I determine that my square root of T90 is 8.3, my actual T90 value is 68.9, because I'm just squaring 8.3. So my T90 value in this instance is 68.9. So if my height of my specimen was 19 mils when I started, I would know what my H value is. This 0.848 is a constant, and it's a constant that is always used for the log time method. And then my T90 value, I calculated to be 68.9. So I could go through and do my calculations to determine what my CV value would be for this data. So it's exactly the same data, and I get a CV value here of 1.1 millimeters squared. What did I calculate it to be here? And here I calculated it to be 0.88. So you'll see there's a little bit of a difference in the CV values. Not huge, but there still is a difference. Anyone have any questions on the root time methodology? The root time I find a little more confusing. Someone must have a question.
Where does the 1.15 come from that you multiply the line?
It's just the methodology for root time. So it's always 1.15. That never varies. So if I gave you another set of data, wherever that initial line intersects your first major grid line after your last data point, you would multiply that time value by 1.15. It's just the process for the root time method.
And I guess there's no way of finding any other T values other than T90 for this?
Correct. So log time is always T50 and root time is always T90, and there's no way to find any other values. Someone way smarter than me has gone through and derived these formulas and done the corrections. I'm assuming these 0.848s and these 0.196s are some sort of correction so that they're representative of the T50 and T90 value. Any other questions? This is another example of just using the root time method. Again, it's just showing you that how to derive the intersection point from your initial linear line with a specific. So here, if we drew our initial linear line, starting it here, oh, sorry. I drew it up here and I have it intersecting my first major grid line after my last data point. So I have it intersecting at 0.014 millimeters. I know the time associated with that is 7.5. So I would multiply that 7.5 by 1.15. So I would know that I would start at a square root of time of 8.6. And then I would draw a linear line here. I'm going to So this represents 8.86, and it's really hard to draw with your mouse. And I'm just going to draw this linear line back to this first data point. And I'm sorry, I know it's not very linear, but where this line intersects my consolidation curve, which is about right here, here, we'll do this right here. I need to make these drawing tools way easier. Where that intersects my consolidation curve, that represents my T90 value. Oh yeah, I guess that's true. I could just use those shapes in PowerPoint. Anyway, so this represents your T90, or your square root of T90, sorry, which is 5 minutes, and then you would square that value to get your T90 value. So your T90 value in this case would be 25 minutes. Yes, I guess I could also just use this. Anyways, anyone have any questions on the process? There, good suggestion, Pavel, I got it. Yeah, there's lots of graphical interpretation. Okay, let's close out of this. Here's the same example. So if here you have exactly the same data as you did, for example, problem 6.6. So the height of your specimen is the same. You have your elapsed time, you have your square root of time, and then you have your compression for the load increment. So here I just plotted it up. You note here I don't have a time of 0 because you can't have a log time of 0. Or sorry, you can't take the square root of 0, so, well, it's 0, but anyways, I didn't plot it up. So this is what our consolidation curve looks like using the root time method. And here I went through in Excel, and the red line represents the linear portion along through the first few data points of my consolidation curve. And I drew it so that I went to a major grid line of 0.8, and that line intersects that major grid line of 0.8 at about 13 minutes. And then I multiplied that 13 minutes by 1.15, and that's about 15 minutes. So the second linear line would start at this data point here, and I extend this linear line back to this data point right here. And where this purple linear line intersects the consolidation curve, I can draw this vertical line down to the square root of time axis to determine what my square root of T90 is. So that's about 10 minutes. So therefore my T90 value was 100. And I could go through and calculate my CV value. And here I got about 1.07 millimeters squared per minute. Any questions? I know we've gone through a lot today. It is on the Learn quizzes. I'm not a huge fan of the Learn quizzes, but that's what we were forced to do this year. Just do your best. I accept a range of values, and I look at everyone's test in person. So if you're in the ballpark, you generally get the marks. So yeah, sometimes you have to use a ruler and kind of estimate, but I'm more looking for process, and I can tell process by the values that are provided. But I would expect a question of this nature. And I don't mean for your quiz that's coming up. I mean for the test at the end of March. A question of this type, a question of calculating your initial void ratio and what would be your void ratio at a specific loading increment. calculating your CC value, your CR value, your pre-consolidation pressure. Those types of questions would be fair game on your quiz that's coming up, because those are fairly consistent with the lab that I posted on Learn. Okay, I'm going to leave the last part of the class up to you guys. I'm sure it's information overload. Has anyone gone through that external load information that I posted on Learn and the example problems and looked at the videos? Okay, the important components of external loads is that you understand the approximate method and you understand the influence coefficients. Both of those methodologies are used quite frequently when you're doing settlement calculations, which we'll be moving on to next week. So you have to have a good understanding of the approximate method and of the influence coefficients. I don't know if you guys want me to go through that today. I somewhat feel like it would be information overload, but I'm open to suggestions. Do you guys want me to do a short tutorial with you guys next week just to make sure you understand external loads? Okay. Okay, what day works for you guys next week? Not Wednesday for me because we have our ARP interviews. What is your guys' class schedule next week? Thursday morning? Just let me check. We're starting to do scheduling for next year. My Thursday morning next week is free. What time would work for you guys? $7:30 in the morning? Unless you want to hear my kids. Yeah, how about we do 9 to 10? Because my kids are at school by then, and then you don't have to listen to them. So we'll do from 9 till 10 on Thursday morning. So we'll discuss external loads, and I have posted some videos, and I'll go through those example problems that I posted. Anything else you guys would like reviewed next Thursday? Okay, I'm going to stop the recording. No, okay, well, we'll schedule Thursday morning next week from 9 till 10. I'll send out a meeting invite for the entire class, and we'll go over external loads. And then if you guys have any questions on the information we covered today, that's fine as well. People are welcome to contact me before Thursday as well. I'm going to open up your tests now. So you'll have to give me about 5 minutes because I have to go in and physically open up all of the tests. But you'll have the opportunity to take a look through your test number 1. I will go to my personal room in case anyone has any questions on their test. Otherwise, have a great weekend. And I'm always here to help, so you know where to find me. Okay, so I'm going to end the meeting and I'm going to go open up your quizzes.